Nari Labs recently published an engineering post claiming they can serve QN3 TTS 1.7b at a sustained 10 requests per second on a single NVIDIA H100 while keeping P95 latency under 50 milliseconds. That 50 millisecond threshold is the time to first audio, or TTFA. Breaking it is what separates a voice agent that feels like a responsive human from one that feels like a lagging conference call. To hit that speed while processing 10 simultaneous streams, their inference stack is generating 630 characters of speech every second. When you translate that throughput into raw hardware costs on a standard H100 rental, it comes out to roughly $2 in compute to generate 1 million characters. This chart shows the gap between raw compute costs and retail API pricing. We have the $2 internal cost against ElevenLabs V3, charging $100. Even looking at a cheaper tier like Cartesia Sonic, the retail floor sits at $49. If independent replication confirms these latency and throughput numbers, paying a 50-fold markup for a hosted API cannot be justified by inference speed or unit economics alone. We recently explored voice AI running directly on a solitary 80-cent microchip. That system required zero cloud dependency and executed a full interaction loop entirely offline. Those two benchmarks establish the absolute poles of the current market. The edge chip prioritizes privacy and rock-bottom hardware costs, while this H100 setup solves for the lowest possible latency on a frontier model. It is important to note the boundaries of the Nari benchmark. That 50 millisecond measurement covers the text-to-speech inference process exclusively and stops the clock before any network transit time is added back to the user. The 80-cent microchip, by contrast, measured the entire physical loop from microphone input to speaker output. If you want to track the exact boundaries of what frontier AI hardware can do the day the data drops, hit subscribe. The remaining defense for paying premium API rates is avoiding three things: owning massive GPU clusters, managing unpredictable capacity planning, or staffing 3 a.m. on-call rotations. The performance gains reported by Nari Labs stem from the architecture of their serving stack rather than the model weights themselves. Standard text-to-speech serving systems execute their tasks in a strict sequential pipeline. Data moves linearly from one processing stage to the next. When these operations are chained together, they form massive, non-preemptible blocks of compute that clog the execution path. If an urgent task arrives, like generating the next audio frame before a stream runs dry, it has to wait in line behind those bulk processing jobs. This structural queuing delay is exactly what causes latency spikes the moment a server experiences heavy concurrent request volume. Scaling up to more powerful GPUs does not bypass this bottleneck. A faster processor will clear the queue quicker, but the structural block remains. Achieving ultra-low latency under load requires dismantling the chained pipeline entirely to eliminate the rigid task blocking. Nari's primary architectural change was taking QN3 TTS and breaking it down into independently schedulable modules. They split the model into 3 distinct components: the talker, the code predictor, and the codec. Instead of chaining them sequentially, they place all 3 modules onto a single scheduling surface managed by one unified scheduler, allowing their order of execution to constantly shift. This scheduler evaluates the microtasks across every open request and ranks them by immediate urgency. Requests that have not yet produced their first audio chunk get absolute priority. This guarantees the lowest possible time to first audio for new prompts. Established streams, which are already returning audio, are ignored until they approach their specific playback deadline. Only then do they become urgent enough to jump the queue. This deadline-driven interleaving means the H100 can pack in efficient batch sizes without forcing individual priority streams to wait behind bulk generation. Feeding this unified scheduler requires stripping away latency from the rest of the software stack. They implemented a state cache codec to change how historical audio frames are handled during generation. A naive text-to-speech implementation reprocesses the entire history of an audio frame on every update, burning compute cycles decoding speech that has already played. By retaining the transformer and convolutional context from previous chunks in a cache, the system applies fresh compute exclusively to newly arrived frames. They also integrate CUDA graphs, capturing the exact sequence of execution steps for predefined batch sizes, removing the overhead of the host CPU repeatedly telling the GPU what to do. They defer the end-of-speech checks entirely until the termination phase is active, preventing the GPU from idling while waiting for the CPU to verify if generation should stop. Together, these micro-optimizations remove the synchronization delays between hardware components that typically degrade real-time inference speeds. The Nari Labs baseline data reveals why these architectural choices are necessary for production. This table shows the 1 request per second benchmark. At minimal load, both VoxServe and vLLM-Omni perform well, sitting between 49 and 57 milliseconds. But when load increases to 6 requests per second, vLLM-Omni degrades to 93 milliseconds, while VoxServe collapses entirely, spiking over 360 milliseconds. The industry habit of quoting latency metrics at a single request per second fails to predict whether an engine will actually survive production traffic. To prove their stack's resilience, Nari ran 5-minute tests using bursty, open-loop Poisson traffic models that mimic real-world user behavior. They also implemented an objective quality gate. Instead of relying on a human listening to the output to catch errors, they routed the received PCM audio through DeepGram's speech-to-text to automatically verify intelligibility. Optimizing for single request speed and optimizing for dynamic load are entirely different engineering challenges, and only the latter matters when you deploy to actual users. For engineers, this stack is fully open source, and the Qwen3 TTS license is permissive enough to stand up immediately. The reference hardware for this benchmark is an H100 SXM instance, which rents for $4.29 an hour on providers like Lambda. This graphic breaks down to $2 per million characters claim. That base number assumes the hardware is running at 100% utilization, around the clock. Consumer traffic does not look like that. A voice agent with daytime peaks and overnight lulls will likely average closer to 20% utilization. At 20% utilization, your actual per-character compute cost immediately multiplies by 5. Then you have to factor in the operational realities omitted from the benchmark: outbound network egress fees, load balancing infrastructure, and the salary of the engineers maintaining it. Self-hosting this architecture is undeniably cheaper than retail API rates, but you trade pure capital expense for a severe operational burden and capacity planning. Evaluating this benchmark requires examining 4 specific limitations disclosed directly in the Nari Labs post. First, the cost comparison uses mismatched categories, equating raw internal compute dollars against retail API prices that naturally include margins and support. Second, Nari acknowledges that the worst-performing baseline engine in their test, SGLang-Omni, had unfinished upstream support during the testing window. Third, the benchmark functions as sales collateral for a vendor, concluding with a call to action for custom deployment consulting. Finally, the latency metric relies on dynamic silence trimming. The stack actively cuts roughly 80 milliseconds of leading silence from the generated audio. This makes their sub-50 millisecond claim an audible time-to-first audio metric. It is a significant engineering feat, but it is not a raw first byte received metric, which changes how infrastructure engineers calculate response times. Because Nari published their entire benchmark harness open source, these caveats are verifiable facts for you to test yourself, rather than terminal flaws in their architecture.